The most dangerous waves in the ocean often arrive without ceremony. They can rise from storm water, from the meeting of swell and current, from the hidden mathematics of wave trains crossing at sea, or from the sudden release of energy beneath the ocean floor. To the person standing before them, they are not equations. They are walls, surges, moving cliffs, masses of water with enough force to bend steel, drown coastlines, and erase the confidence of ships built to cross oceans. For centuries, sailors described waves so large that listeners on land treated them as exaggerations. Men spoke of walls of water appearing out of rough seas, striking vessels with impossible height, then vanishing back into the moving surface. The stories were repeated in harbors, logbooks, and maritime memory. They sounded like folklore because the ocean rarely left proof. A ship that sank could take its evidence with it. A wave that killed could leave no permanent scar on the water. Then instruments began to confirm what fear had carried for generations. On January 1st, 1995, the Draupner platform in the North Sea recorded a wave around 25 meters high, far larger than the surrounding sea state. The data mattered because it transformed the rogue wave from sailors' nightmare into measured reality. The ocean had produced a wave beyond expectation, and a machine had caught it. From that moment, the sea became mathematically stranger. The word wave sounds simple, but the ocean uses it for many kinds of danger. A rogue wave can rise in the open sea as a steep and sudden giant, threatening ships far from land. A tsunami can cross an entire ocean basin after an earthquake, landslide, or volcanic collapse, then become devastating as it reaches shallow water. A storm surge can push the sea inland during a cyclone, lifting water into towns, ports, roads, and homes. A sneaker wave can rush farther up a beach than expected and pull a person into cold water within seconds. These events share water, motion, and force, yet their origins differ. Wind builds ordinary waves across the surface by transferring energy into the sea. The longer and stronger the wind blows across open water, the larger the waves can become. Currents can oppose them and make them steeper. Storm systems can organize enormous fields of swell. Earthquakes can move the seafloor and displace entire columns of water. Atmospheric pressure and coastal shape can turn storms into flooding machines. This variety makes the ocean difficult to fear correctly. People often picture the dramatic breaking wave, the visible crest, the cinematic wall. Some of the deadliest water does not look like that in deep ocean. A tsunami at sea can pass beneath a ship as a long, low movement. A storm surge can arrive as rising water rather than a single crest. A rogue wave can appear during severe seas, strike once, and disappear. The danger changes its form according to physics, depth, coast, and weather. Before modern measurement, extreme waves occupied an uneasy place in science. Sailors knew the sea could produce them because ships had met them. Scientists could not easily verify the size or frequency because the events were rare, short-lived, and widely scattered across the world's oceans. The sea is enormous, and instruments can only watch small parts of it at any moment. This made the most violent waves seem almost evasive. The Draupner wave changed the discussion because it had data. The platform's instruments measured a wave that towered above the significant wave height. That phrase matters. Significant wave height is an average measure of the higher waves in a sea state. It helps describe roughness, but it does not capture every individual crest. A rogue wave is usually defined by its relationship to the surrounding sea, often more than twice the significant wave height. Its danger lies in surprise as much as scale. After Draupner, researchers took older reports more seriously. Satellite observations, buoy measurements, ship encounters, and platform data began to suggest that rogue waves, while rare at any single location, were more plausible than traditional models had allowed. The old idea of the sea as statistically predictable at the extremes had to be refined. A vessel might be designed for severe conditions, yet still meet a single crest outside expectation. The ocean was reminding engineers that rare events matter. To understand dangerous waves, one must think of the sea as a moving field of energy. Wind creates wave systems. Distant storms send swell across thousands of kilometers. Local weather adds shorter, steeper waves. Currents bend, slow, or compress them. When wave systems meet, their crests can briefly combine, making one wave much higher than its neighbors. In some conditions, energy can focus into an individual crest that seems to rise out of the surrounding disorder. Opposing currents are especially important in certain regions. When waves travel against a strong current, their wavelength can shorten and their steepness can increase. This can create dangerous breaking seas, especially where storms, currents, and underwater topography interact. Places such as the Agulhas Current region off southern Africa have long been known for extreme conditions because large swell from storms can collide with powerful currents moving in the opposite direction. There are also nonlinear processes in wave physics, meaning waves do not always behave as simple independent shapes, adding together cleanly. Under certain conditions, energy can transfer among waves in complex ways. Researchers continue to study how these mechanisms contribute to rogue waves in real oceans. The important point for a ship is direct. The ocean surface can briefly organize itself into something far more dangerous than the surrounding pattern suggests. The Dropner wave remains one of the most famous ocean measurements because it gave a precise record to an old fear. On New Year's Day in 1995, the North Sea was already rough. Offshore platforms are built for harsh weather, and workers in such environments understand that the sea is never gentle for long. Yet the recorded wave rose far above the expected sea state, reaching roughly 25 meters. It struck the platform and caused damage. The wave became a landmark because it proved that a rogue wave could be measured in the open ocean under real conditions. It was not reconstructed from memory. It was not inferred only from wreckage. It existed as a signal, a trace, a numerical fact. The sea had produced the kind of event that many had doubted, and the data remained after the water moved on. Dropner influenced engineering and risk models because structures at sea must be built with assumptions about extremes. If the most dangerous waves occur more often than expected, the design philosophy must change. Offshore platforms, ships, and coastal systems all depend on estimates of rare events. A small error in imagining the tail of risk can become enormous when millions of voyages, years of operation, and thousands of vessels are exposed to the ocean. A dangerous wave does not kill by height alone. Its steepness, speed, braking behavior, and angle of impact all matter. A long swell can lift a ship over time. A steep breaking wave can strike like a collapsing wall. Water is heavy, and moving water at ocean scale carries a force that ordinary experience does not prepare us to understand. A cubic meter of seawater weighs more than a metric ton. When thousands of tons move together, the result is closer to architecture in motion than to the water we pour into a glass. Ships are built to flex, climb, roll, and survive severe weather, but they are vulnerable to unexpected loads. A wave striking the bow can damage plating. A wave breaking across the deck can tear away equipment, smash windows, destroy lifeboats, and flood openings. Containers can be ripped loose, crew can be injured or swept away. Even large vessels are small compared with a sea that rises above their working decks. For smaller boats, the danger is immediate. A fishing vessel caught beam on by a steep breaking wave can capsize. A yacht in heavy weather can be rolled. A rescue craft can be overwhelmed. In such moments, seamanship matters, but physics sets the limits. The ocean does not respect courage, experience, or panic. It applies force through mass and motion. Among the most dangerous waves ever recorded, tsunamis occupy a separate realm of fear. They are often born from undersea earthquakes that shift the seafloor and displace huge volumes of water. In deep ocean, a tsunami may have a small height at the surface but an enormous wavelength, traveling at jet aircraft speeds across entire basins. Its danger is stored in length, speed, and volume. As a tsunami approaches shore, the seafloor rises beneath it. The wave slows, compresses, and grows. Water that was spread across a vast wavelength begins to pile up. The result may be a fast-rising flood, a turbulent bore, repeated surges, or a series of destructive waves. The first wave is not always the largest. The sea may withdraw before returning, exposing the seabed in a way that tempts the unwary into fatal curiosity. The 2004 Indian Ocean tsunami and the 2011 Tohoku tsunami showed the scale of disaster that long waves can produce. These events were not dangerous because of one beautiful crest. They were dangerous because entire coastlines were struck by moving water loaded with debris, boats, buildings, vehicles, and shattered infrastructure. A tsunami turns the ocean into a horizontal force that keeps arriving after the mind expects it to stop. Storm surge is another expression of ocean danger. During powerful tropical cyclones or intense storms, winds push water toward the coast, while low pressure allows the sea surface to rise. Coastal geography can amplify the effect, especially in shallow bays, estuaries, and funnel-shaped shorelines. When surge combines with high tide and breaking waves, the result can be devastating flooding. Unlike a rogue wave, storm surge can last for hours. It does not need to appear as a towering crest. It raises the baseline of the sea until streets, homes, fields, and ports are inside the ocean's reach. The water carries floating debris, sewage, fuel, shattered wood, metal, and mud. It damages foundations, contaminates drinking water, and traps people who waited too long to leave. Storm surge demonstrates a different kind of danger from waves offshore. It is a coastal invasion, a temporary rewriting of geography. The line between land and sea moves inland, and everything built on the assumption of a stable coast becomes vulnerable. As sea levels rise and coastal populations grow, the danger of surge becomes more severe in many regions. The records of past storms are warnings about the future shape of risk. Many lethal waves never make global records. They happen on beaches, rocks, harbor walls, and coastal paths. A person watching the sea may see several moderate waves and assume the pattern is safe. Then a larger set arrives. A sneaker wave rushes farther up the shore, knocks people down, pulls children, adults, pets, logs, and loose objects into the surf. Cold water, rip currents, and impact against rocks can turn a few seconds into a fatal event. The coast is dangerous because it feels accessible. A cliff path gives the illusion of distance. A beach gives the illusion of softness. A harbor gives the illusion of control. Yet waves generated by storms far away can arrive under clear skies. Long-period swell can carry energy from weather that no one on the beach can see. The ocean's memory is larger than the local weather. Rock fishermen, storm watchers, photographers, and walkers are often caught because they stand where rare waves can reach them. The sea does not need a record-breaking height to be deadly. It only needs enough force to break balance and enough retreating water to pull a body into turbulence. For the individual human being, the most dangerous wave may be less than a few meters high. Climate change complicates the future of dangerous waves. Warmer oceans can influence storm intensity, rainfall, and coastal flooding risk. Rising sea level allows waves and surge to reach farther inland from a higher starting point. Even when the waves themselves are not dramatically taller, the damage can increase because the coast is more exposed. A storm that once flooded only low ground may reach neighborhoods, roads, and infrastructure that previous generations considered safe. Changes in storm tracks, wind patterns, sea ice, and ocean circulation may also affect wave climates in some regions. Scientists study these changes with buoys, satellites, hindcasts, and climate models. The results vary by location, but the general concern is clear. Coastal risk is shaped by both ocean behavior and human settlement. More people, more buildings, and higher seas create greater consequences when extreme waves and surge arrive. The record of dangerous waves should therefore be read with caution. Past extremes are guides, not boundaries. A seawall designed around yesterday's water level may be too low for tomorrow's surge. A coastal road placed above historic floodlines may become vulnerable as baselines shift. The ocean is dynamic, and the human world has built too much at its edge to ignore that motion. Modern technology has improved our view of extreme waves, but it cannot see everything. Satellites measure sea surface height across broad areas. Buoys record local motion. Offshore platforms collect detailed data. Radar scans wave fields, and ships report encounters. These tools have revealed a more complex ocean than older models suggested. Still, the most extreme individual waves may form and vanish where no instrument is present. This creates a strange relationship between records and reality. The largest wave ever measured is not necessarily the largest wave that has occurred. It is the largest wave that crossed the right instrument, survived data checks, entered the scientific record, and became known. The ocean has no reason to place its greatest events near our sensors. Much of its violence remains private. The same is true for many losses at sea. A ship disappears, and investigators must work from weather reports, last communications, debris, cargo records, and probability. A rogue wave may be suspected, but certainty can sync with the vessel. In the deep ocean, the event can be both cause and witness, then vanish into the same water that produced it. The most dangerous waves ever recorded are more than spectacles. They expose the limits of prediction, design, and human confidence. Dropner showed that the open ocean could produce sudden giants beyond traditional expectation. Tsunamis showed that the movement of the Earth itself could become a wave crossing entire oceans. Storm surges showed that weather could lift the sea onto land. Sneaker waves showed that danger could arrive on a bright day without drama in the sky. The ocean remains powerful because water at scale is a geological force, a weather system, a moving mass, and a memory of distant storms. It can carry energy across basins. It can focus that energy through currents and coastlines. It can destroy through impact, flooding, debris, cold, and retreating flow. It can look calm shortly before it becomes lethal. Every generation builds better instruments, better models, stronger ships, clearer warnings, and safer coastlines. These efforts save lives. They also reveal how much complexity remains. The sea is not a static enemy waiting to be defeated. It is a planetary system in motion. The most dangerous waves are the moments when that motion becomes visible, when the surface rises into a shape large enough to remind us that the ocean is one of Earth's oldest powers.